Hello and welcome to lecture number 4 about this paper by Albert Einstein. The paper is called On the Electrodynamics of Moving Bodies. In this video, I am going to derive both of these equations which appear in this paper. So let's get started. So let's start with the first equation. The first thing that I'm going to do is multiply the denominator by the left-hand side. So let's do that algebra. So I multiplied TB minus TA times uppercase V minus lowercase v, where uppercase v is actually c for the speed of light. So when you multiply this c by TB minus TA, you get TB times C minus TA times C. And similarly, when you multiply negative lowercase v times TB, you get negative TB times lowercase v. When you multiply negative v times negative TA, you get a positive TA times v. Next, I'm going to do the same thing for the left-hand side and the denominator. All right, so when you do that, you end up with a positive TA prime times this positive C, remember capital V is C, minus TB times C. And now we just need to distribute this lowercase v to both TA prime and negative TB. So we have done the necessary foiling. Why did I do this foiling? Well, now we can look at each of these terms and assign a physical meaning to each of them. And notice that each term is a time times a velocity. As you can see, there are 3 unique time values, TA, TB, and TA prime. And Einstein says or defines that each of these time values are in the stationary frame. So let's draw what happens at time t sub a with respect to the stationary frame. Here I am drawing point A as well as point B. And this corresponds to time t sub a. At time t sub a, light is emitted from point A. So I can maybe put a dot on point A to symbolize that. I did put point B at an arbitrary location, but this particular situation doesn't involve point B, so I'm going to erase it so that we don't do anything incorrect. Now I'm going to do the same thing for time TB. So here we have time TB and the corresponding physical situation with light being reflected at point B. And I have not drawn point A. And finally, I'm going to draw the physical situation corresponding to TA prime. We are in the stationary frame, and the physical situation that we are looking at involves a line segment that is moving, I'm going to say that it's moving to the right so that I can draw the situation here. So point A should have moved by some unknown amount. Actually, it's known. It's related to the velocity of the moving frame, lowercase v. All right, so the third line involves light arriving back at point A at time TA prime, and in blue I have drawn the line segment AB for each of the 3 times, assuming that the line segment does not change in length. The line segment definitely should not change in length in the moving frame. In the stationary frame, it is questionable whether the length stays the same or not. So if it doesn't, then this could be interpreted as a qualitative drawing. Now let's try to understand the terms involving the speed of light. In particular, when the light travels from point A to point B, how far does the light actually travel? Well, it travels along this line here and also this extra distance as well. But we need to be careful because even though point A is in this diagram as well as this diagram, T sub A only refers to this point. So when we say C times T sub A, we're referring to this time and this position. Or maybe position isn't the best word. We're just referring to this particular event. So how far does light travel in the time interval TA to TB inclusive? It travels from this point all the way to this point. So this distance is equal to TB minus TA. Now let's think about the return trip of the light from point B back to point A, or from time T sub B to time T sub A prime. So at time T sub B, the light is here. At T sub A prime, the light is here. This means that during the time interval of TB minus TA prime, the light travels a distance equal to that. Now here's the interesting part. We have 4 terms here. We have 4 terms here for the phenomenon from TA to TB. And similarly, from TB to TA, we have 4 terms, and those 4 terms are also accounted for. I'm going to modify this diagram just a little bit because we have separated the path of light into 2 parts when the light's traveling to the right and when the light is traveling to the left. We don't consider the process as a whole, so we don't need this. We can instead record the distance the line segment has traveled during the second time interval, which is TA prime minus TB times V. And we still have 8 terms, so that is good. And now the difficult part is over. Now we just need to do a little bit of subtraction to find what the line segment AB is equal to. Let's do this part first. All we need to do is say that the line segment AB is equal to the larger distance, which is this one, CTB minus CTA, and we need to subtract the smaller distance to get this distance. So we can say minus VTB, and there's already a minus here, so when I subtract a negative, I get a positive, so it's going to be plus TAV, plus TA lowercase v. So that's the line segment for the first phenomenon of light traveling from point A to point B, while there's movement of this line segment. Now we can also calculate the line segment based on the second process and these 2 other distances that we have calculated. We just need to use geometry. So let's zoom in here. In order to get this entire line segment here, we need to add this line segment with this line segment. So we just need to add this quantity with this quantity here. What do we get? We get the line segment AB when fully distributed is CTB minus CTA prime plus VTA prime minus VTB. Now let's compare these 2 line segments to the original 2 expressions that we wrote out here. Are they the same? This is for the first process, CTB, CTB minus TAC minus TAC minus VTB minus VTB plus TAV plus TAV. Yes, they're the same for this first process. For the second process, we have TA prime C. We have a minus here. Okay. Interesting. 1 second. That's because I made a mistake. The time interval is not TB minus TA prime over here. It should be TA prime minus TB because TA prime comes after TB. We want to use positive time differences, which is what we have always been doing. TA prime minus TB, so that we get a positive distance instead of a negative distance, which doesn't make any sense. So that makes our negative C TA prime a positive. So basically any term with C becomes a negative of what it was. Sorry about that. And now we can compare. So negative TB times C, negative TB times C, TA prime times C, TA prime times C, TA prime times V, positive, TA prime times V, positive, and negative TB V, negative TBV. So they are exactly the same, which is rather great that we have verified these these two equations because AB is the same thing as RAB, which is the length of the rod that is moving as viewed from the stationary frame, or the length of the rod, the length of the moving rod in the stationary frame. So we have verified these two equations. I did make an error along the way here, but we fixed it. And I hope you learned something from this video. Thanks for watching.